President Haldia Bajalacha Welfare Organization Sri Dilip Kumar Vera and Dr. Akhil Chandrakar, convener of this international conference. So I feel honored and privileged to be here with you on the inauguration ceremony of this international conference, and thank you to the organizer for inviting me and giving me opportunity to say something on nanotechnology. What I feel basically nanotechnology is the manipulation of material characteristics. So every time you will hear that nanotechnology, basically it is a nanomaterial science. So if you design any material which lies in the nanoscales, definitely the material property will be changed. And that material, nanomaterial will behave differently. And in this arena, nanotechnology is a hot topic for both the academia, industrialists and researchers. And nanotechnology has diversified applications, but one thing we must remember, definitely nanotechnology has some benefits for betterment of health or safety of the human health or environment. At the same time, nanotechnology is associated with the toxicity also. I am working actually in the field of drug delivery. So the conference come up with the theme that is nanotechnology for better health, safety and environment. So nanotechnology for better health, in that sense, suppose we are using a tablets. So when we are using a tablet, that is not a nanotechnology, that is a matrix system. But drug enters into our blood. But the drug has no specific targets. It is non-selective, you may say. But what is the utility of nanotechnology? If we design a material that in the nanoscale, but if we attach a ligand that specifically targets the specific diseased cells, thereby avoiding the other normal cells of our body. So that means nanotechnology offering safety, because you are safeguarding the other normal cells that is targeting to the disease cells. That's why nanotechnology is for better health. So, and also providing safety. So under this scenario, that is in these decades, several works are going on for some specific end-use applications of this nanotechnology, and some several speakers are there, application of nanotechnology. And once again I thank you to the organizers, and I wish a grand success to this conference. Thank you.
And dignitaries in the land, and the audience, mainly from this institute, who are the students. I think this conference has twofold advantages to us. One for the students, another for the teachers like me. Students at least get their directions, some ideas about the nanotechnology, its various branches, its development, its application fields, both in the research areas and in the technology. And for us, generally we attend conferences, most of the speakers are from the academic institutes, but here I can see there are some persons, technological applications of this nanotechnology. This field started, I think, from the great work of Richard Feynman. There's plenty of room at the bottom, I think. So the level has gone down, with a decrease in size. The properties starting from electrical, optical, dielectric, magnetic, all the property changes. How these changes and how to capitalize those properties in the industrial field for the upliftment of our society. That is the main thing for us. It is a challenge for us. But at the same time, I can give you one knock. I got an image in the WhatsApp. After having lunch, there is a photograph of a family. 9 or 10 altogether members were there. Each one having their mobile and enjoying themselves. No gossiping after the dinner lunch. Okay? No Golpoda Durasur, no Thakurmar Jhuli, no Tenida. We have lost all those things. Maybe for the betterment, we are ready to sacrifice. But technology and our social life has to be mixed somewhere. It is our duty being an old man. Thank you.
Thank you, Dr. Shanut Kormakar, Associate Professor of Jadavpur University, to deliver few words.
All the audience, students, ladies and gentlemen. So, this international conference, I feel technology and all the speakers and guests, they have already said what is nanotechnology, usefulness and all. And I will not take much time for that, so I will not say at this moment. So all these technical aspect of nanotechnology. But what I would like to say is, so I feel that for this type of conference, students and other scientists who are working in this field will get benefited. Okay, so the interaction is more important, and we will also come to know that what is going on. There are several aspects that we have already, people have already told you that there are several aspects of nanotechnology. So one can link, like it's an interdisciplinary subject, so one can link from physicist to chemist to biologist, some engineers, doctors. So all of us, we are working in this field. So one can actually, the subject can be linked from technology to basic science. Okay, so we will listen to some basic physics, basic chemistry, and technological aspect, also some kind of applications for safety in human health and environment. Okay. I wish this conference will have great success, and with this few words, I'd like to thank again the organizers and also the audience for giving me the opportunity to talk to you in this conference. Thank you very much.
This time, we aspire to acknowledge the talent of the students who have been struggling and facing many challenges and difficulties to be pioneers. In fact, that's all because of their own perseverance, constancy, and that they're selected as champion. So to appreciate their hard work, I would like to call upon our chief guest, Shri L.C. Mishra, to felicitate them with some amount and a memento as an honor of Shirish Chandra Memorial Award. On behalf of them, can take the prize and the memento. Please give them a big hand. I congratulate and appreciate the students and their parents, chief honorable dignitaries, with a memento, because we are really glad that in spite of their busy schedule, all the dignitaries have taken out their time to attend this ICMT 2019. So first I would request Dr. R. N. Jana to facilitate Dr. Manush Kumar Bhuiya with a memento. Dr. R.N. Jana to facilitate Dr. Shunirmal Jana with a memento. Request Dr. Akhil Chandra Kaur to facilitate Dr. Shobhu. Now I will request Dr. R.N. Jana to facilitate. I will request Dr. Akhil Chandra Kaur to facilitate Dr. Shanut Kaur. Now I will request Dr. Now I would request Dr. Sanjeev Jana with a memento. Now I will request Shri Deepak Dr. Akhil Chandra Kaur with a memento.
Honorable Chief Guest and other all honorable dignitaries, speakers and students and professors. I am very privileged to give me opportunity or give me for vote of thanks. Today's international conference on nanotechnology. The theme is nanotechnology for betterment of the health and safety. First, I give thanks to our chief guest, Sri A.C. Mishra, EVP and the plant head, MCPI Private Limited. He has told that about 40 years he has given service to ICL and petrochemical industry. How the importance of safety. Nowadays, safety is a very prime part of the industry. He focus on fire and safety implementation part. Here we have different types of workshop, conference is going on here and there. But he focusing mostly on the implementation part. If it is only closed in the room, it will not be perfect. So we have to focus on its implementation part. And he is focusing on the without safety, or what is without safety one industry cannot run, and behind this lack of knowledge or ignorance of the employees. So he focused for the safety comes from the ourselves or self. Then it comes to the industry and comes to the safety or nation. Then he focused on the health, how a healthy person goes to equipment, rope, how it can be improve our this nanotechnology helps in our industry and different type of environment, solid waste management, sewage treatment plant. If knowledge and imagination comes and get together, it will help to betterment. This nanotechnology gives a betterment for health, safety and environment. I also thank Mr. Sadra, Assistant Professor, Indian Institute of Technology. He is focusing on his subject cancer technology, how nanotechnology helps in cancer technology. I again thanks to Professor Twin Sadra. Research work is so lower in India. He has given some reasons. Interdisciplinary action on basic science and research with industry. These three he has combined with it, and these will help. I thanks to Dr. Sabyasachi Maiti, Associate Professor, Indira Gandhi National Tribal University. He has told about more focusing on drug therapy or drug about the twofold. The students and professor can help this seminar because here not only the academic professor are present, also the industrialist and industry person also present. These interaction with the students, professors, industrialists, researchers, interaction with each other, it will help to betterment our society. And I thank to Dr. Sanat Karmakar, Associate Professor, Jadavpur. He has told about the basics of nanotechnology, and also he has given focus on students, scientists, and get inspiration more from the interaction with each other and interaction with the basic science and technology, and it will help in different research works, and it will help in the safety, health and environment system. I also thank to our convener, Principal Madam and Patron Arin Jana, and I thanks to Sri Deepak Ponda and Aditi Sinha. It is I again thanks to all other members of this institute and all the students and the guests. And I hope these 2 days international conference on nanotechnology will be great success. And I again thanks all the chief guests and all the dignitaries, speakers and students and this institute's professors and students. Thank you again.
Thank you, sir. We have come towards the conclusion of morning session of ICT 2019. Thank you so much all the honorable respected dignitaries for having their time for ICT 2019. Once again, a big thank to all of them. Today we are having plenary lecture session, technical session, poster session. So please be with us. Your cooperation is highly solicited. So all of you can proceed towards a tea break.
As you can see, from the Stone Age to this computer age, PV cells, wind energy, thermal, geothermal energy. Okay, so these are very less amount compared to the fossil fuels. Fossil fuels. So what is the solution right now? We can use solar energy. If you have only 1 hour of solar radiation, the carbon dioxide, which is one of the major greenhouse gases, It can harvest solar energy, okay, solar energy and carbon dioxide and water. It can form the sugar, which is the basic food unit of our planet. And here we have photosystem 2 and photosystem 1. Photosystem 2 and photosystem 1, basically P680 and P700 nanometer wavelength. It can harvest solar energy and it split water by 4 electron and 4 hole oxidation reactions. It forms the protons, and this electron basically shuttle through these redox mediators like plastoquinone to plastoquinoline and cytochrome B6F and several redox mediator. This electron can go to store the NADPH. So we want to emulate this photosynthesis by chemical reactions. With oxygen, it can generate electricity, yes, and at the same time it's a carbon neutral. There is no carbon, there is no pollutions. So hydrogen and oxygen reacts, make electricity and subproduct it water, and again you can split water, you can get hydrogen. So it's a recycle. So the future energy is that we need to take 1 tank of water in the car, split water, hydrogen, oxygen, combine with fuel cells, hydrogen fuel cells, use the hydrogen as a fuel and subproduct with the oxygen. So hydrogen and oxygen both can be used in the fuel cell, and you use the solar light and you can use the car. Even you can generate electricity. Scenario of hydrogen, we are using hydrogen in industry. We are making ammonia, we are making fertilizers. So in the fertilizers we need large amount of ammonia. How we are making? We are making by Haber-Bosch method, which is energetically not economic, but still we are using for fertilizers. So this hydrogen can be generated by water. Current scenario is that this hydrogen is coming from steam reforming reactions. What is steam reforming? We can use monoxide and hydrogen. And then reactions, which is really important reactions, where reaction of carbon monoxide with steam generated by steam reforming. Also we have dry reforming reaction where we don't use water instead of water. So another thing is that by using this synthesis gas, we can use Fischer-Tropsch synthesis, where you can make the hydrocarbons, any kind of hydrocarbons. You can see the polymers. PET bottle, polyethylene terephthalate is a polymer. You can see many things, aircraft, this shoe, everything made of mostly polymers. So these polymers can be made from petroleum or hydrocarbons. How to make this hydrocarbon? So it's very simple method. We can take hydrogen and oxygen, we can get water and electric power and heat. This is a simple schematic diagram of fuel cell, hydrogen oxygen fuel cell. This is the future. What I am telling is this is the future of energy landscape. Here you can see we have a cathode and anode and an electrolyzer. In general we used to use polyelectrolyte membrane electrolyzer, where we can feed hydrogen. Hydrogen acts as a feed here. It is an anode where hydrogen comes, and this hydrogen split into proton and electron. This proton can permeate through this electrolyte membrane towards the cathode, and in cathode reduction occurs and we feed oxygen from the cathode side and it generates water molecules. And this electron, because of splitting of hydrogen, it generates protons and electrons. This electron can shuttle through this external circuit and generates electricity. So this is the future energy. So what we can do is that we can take water, split hydrogen and oxygen and combine these fuel cells, so we can complete the circle. So there is no pollution, there is no carbon. Simple water can generate electricity. I will give one example, that is Toyota Mirai FCB. Toyota Mirai, Toyota company in Japan, they started this fuel hydrogen car, that is Toyota Mirai fuel cell vehicle car. It has almost 540 miles range. Recently they started this hydrogen car. No need of diesel, no need of petrol. Only water is sufficient to drive this car. Okay? But problem is,
The breaking part of hydrogen
yes,
into proton and electron, how much energy? 13.6 electron.
yes.
That is supplied by this part. But which source?
Here, fuel cells.
That hydrogen is broken into two parts now. It's plus and electron, right? In the left hand side.
Yes, yes, yes.
So the amount of energy supplied there and the amount of current we are getting through that electrical part.
Okay. So we, yes, we are using catalyst. Varieties of catalyst we can use. Fuel cell we use.
Using catalyst, the
Yes, as well. So what?
Okay, we will discuss later on after your comment.
Yes. So the problem for the hydrogen is that hydrogen is very light, okay, and making liquid hydrogen is very tough. Recently, in 13 December, Kawasaki heavy vehicles, they started this Swiss of Frontier, world's first liquid hydrogen carrier ship at minus 254 degrees, and this is basically a ship which can carry liquid hydrogen. It's from Australia to Japan. So Swiss of Frontier, world's first liquid hydrogen carrier ship. It's I don't remember exactly how much. It's a few hundred tons of liquid hydrogen it can carry. The problem is that hydrogen is very dangerous. It can blast it. So to seamless transformation of hydrogen production to the storage and the usage is really a difficult task. So people are working on making hydrogen, at the same time storage of hydrogen and usage of hydrogen. So we need to be we need to have very good safety, or else it will be a dangerous thing. Okay? So we can split cathodes and anodes. You can split water. Very simple. You need to use some potential. You need to use some light current, and then you can split water and it can form hydrogen and oxygen stoichiometrically. Only 77%, because water splitting, as you can say, because the bond electron volt band is 1.23 electron volt. So the energy efficiency is 1.23 divided by 1.6 divided by 1.23 into 100. So thereby we can get 77% energy efficiency, because input is 1.6 volt, little bit higher. 1.23 is the limit of this. Yes. So now the hydrogen here $3 per kg, but people are using this electrolysis to make hydrogen and oxygen. Another way is that thermal decomposition of water. We can split water by two different ways. One is the nuclear thermal and another is the solar thermal. By two different ways we can split hydrogen and oxygen. But thing is that both these cases, if you think about nuclear thermal, you need to make nuclear power plant in coastal area, and people are afraid of radioactivity. So we cannot make all coastal area the nuclear power plant. And also compared to the diesels. Another process is the radiolysis. We can use alpha, beta, gamma radiations to split the water molecules. We can get hydrogen and oxygen, but it is very costly. It is not economically effective, so we don't use it. Most important thing is that photoelectrochemical water splitting. By two ways we can make. One is the photovoltaic device, PV cell with electrolyzer, PV electrolyzer, electrodes, and shine the light on the electrodes. Thereby we can generate the current and split the water. So this is called photoelectrochemical electrolyte cell. This is mostly people are trying to do this because we use semiconductor catalyst. Another important thing is that photovoltaic device. What is it? We have a solar panel. We can use silicon solar cell, silicon single crystals, and we can shine light here in this PV cell. It can generate electricity, and thereby we can split water, hydrogen, and anode here. So cathode making hydrogen and anode making oxygen. So it's a demonstration of how we can split water into hydrogen and oxygen. You can see, and we reported here. Scientifically is hydrogen evolution reaction. As you can see here, two holes can oxidize and forms oxygen, and two protons are reduced to make a molecular hydrogen. This is called hydrogen evolution reactions, and this is called oxygen evolution reaction. The total reaction is water half-O2 plus hydrogen. As you can see here, the Gibbs free energy change is equal to 237.2 kilojoules per mole, which is energetically aphil reactions. Which is a energetically aphil reaction. As you can see here, the product reactant is here, product is here. So it's a energetically aphil reaction. So to make this reaction, we need to have catalyst which can reduce the activation energy. Thereby we can split the hydrogen and oxygens. So we need 1.23 electron volt to split the water, which is corresponds to 1100 nanometer, which is in the regime of infrared radiation. Solar radiation, only 5% comprises of UV light. Only 5%. Okay. So mostly we have visible light and infrared. So if you want to use the solar light, you need to have a catalyst which can harvest solar energy in the visible range, not in the UV range. If you see this 1100 nanometer corresponds to 1.23 electron volt, this is not kinetically favorable, because I will discuss later on. So is it possible to make, and you start it and you will generate hydrogen and oxygen. This is the future of energy landscape. This is the future, what I am telling you. As you can see here, we have a water, a beaker of water. We have some photocatalyst on it, and you sign permeability. So this is invented by Professor Kazunori Tome. He is from University of Tokyo. I worked with him. So it's possible. So by using water and sunlight, we can make hydrogen. Now, so we have several stages. For example, light absorption. We need to have light absorption, then exciton generation, and then exciton breaks, and it forms charge separation, and then charge migrates to the co-catalyst here we used, charge migration, and then surface reaction for water reduction and oxidation reactions. As you can see here, sunlight, sun shines, and then, oh sorry, so exciton generates, and then charge separation and migration to the co-catalyst. Electron goes to the reduction side, and then hole goes to the oxidation side, and it forms, here it forms a hydrogen, here it forms a oxygen. Next stage, so the problem associated with this photocatalyst is the recombination. Recombination we want to do is that we need to separate the charge, and we need to use the free charge carrier for the reduction and oxidation. But if it recombines, we cannot use the electrons and holes, right? So this is the pitfall for these photocatalytic reactions. So these are the components for photocatalyst. One is the photocatalyst, co-catalyst. We generally use the platinum or ruthenium noble metals, redox species. Here I use sacrificial donor. So semiconductor properties, as I said, catalyst is semiconductor band gap and band positions, charge separation, surface area is really important because photocatalyst is a surface photoredox reactions. More high surface area favors the catalytic activity. Particle size is really important. Today's seminar is nanomaterials, so we generally use nanoporous materials. Systematically deposit oxygen evolution catalyst and hydrogen evolution catalyst and gold surface by atomic layer depositions. We can make an interface between the hydrogen evolution catalyst and oxygen evolution catalyst. So photocatalyst, to see it is very simple, but it is very complex because it involves physics, solid state physics, chemistry, biology, many things. We need to combine. So I made it 6 gears. If you stop one gear, another gear will be stopped. So we need to have a balance between the 6 gears, then only you will get hydrogen. You know, when I joined in KAUST, people are saying hydrogen evolution is impossible. You need to take him, then only both of you reach to your destiny, right? So you need to pull it. You need to pull it so that we can reach this hydrogen. So time scale starts from femtosecond to second. For example, as I can say, photon absorption, it's a regime in the range of femtosecond. But if you consider the mass transfer, which is the hydrogen binds with the catalyst and then takes away from the catalyst, which is in the order of second or nanosecond. So we need to prototypical or for make a practical application for photocatalytic applications. This is really tough, really tough. So here I have shown varieties of inorganic nanomaterials, inorganic semiconductor, better to say, which are found in any common solvents, and optical properties band gap is 2.7 electron volt. As you can see here, it was first invented by Professor Domain 2009 in Nature Material from University of California, Los Angeles. We did the theoretical calculations to understand how the structure works. And this is the possible structure of carbon nitride. We demonstrated by, this is the TEM analysis nicely, and this is a nano rod kind of structure. But it's not working. Hello. And we published this work in Angwansi Chemi as a hot paper in 2014. So we used to see the plants. If you observe very nicely the plants can harvest solar energy. See the structure.
Take water oxidation towards green energy fuel like hydrogen generation, and giving so detail, give you more time, it will be better. So it is now open for discussion, but due to time constraint, very few questions are requested. Please, if you have any questions or queries. Okay, I have one question. In water oxidation reaction, the efficiency is now not so good. It is like 1 or below that.
ST8. You are talking about solar to hydrogen conversion?
Right. So, how? What is the future of this energy resource?
Okay, oxygen is stoichiometrical, but the hydrogen and oxygen again recombine to form the water. This is the big problem. Another thing is that photocorrosion of the semiconductor. We are shining the light to the photocatalyst, and most of the photocatalyst corrodes. It gives very good efficiency, but it photocorrodes. Thereby, after few hours of reaction, photocatalyst damaged completely. So, recent trend is that coating, surface coating. As I showed this thin film, hydrogen can penetrate, oxygen cannot penetrate. Thereby we can be circumvented by using this coating of chromium oxide.
Thank you very much. So, I yeah. So from
Hello. And the single cell therapy and diagnostics, especially we do that electrochemotherapy.